This is a simple example, numerical example involving force vibrations and resonance. So let's write it out. So we have a undamped mass spring system. And let's say, even though we derive an expression for F naught sine omega t, let's look at F naught cosine omega t. Okay. Okay. So let's say given one, mass equals, let's say 1 kilogram, F naught equals 100 newtons, and omega equals, let's say 3 hertz. And the question part 1 is determine stiffness K at which the system will exhibit resonance. Resonance at the given omega. Okay. We might alternatively say K at which system has maximum force amplitude, which is the same as resonance. So this is equivalent to saying has maximum force response amplitude. Okay, so we might phrase a question like this or like this potentially. So that's question number 1. Question number 2 is if K equals 5 Newton per meter, determine force response amplitude. Okay, so those are the questions. So question 1 is resonance. The conditions for resonance is that omega equals omega n, the natural frequency. The natural frequency is square root of k over m. Omega is given to be 3 hertz, and that's going to be equal to square root of k over m. So square both sides. So we have 9 equals k over m, or k equals 9 times m, where m itself is 1 kilogram. So you have 9 Newton per meter is resonance. So k equals 9 Newton per meter. This, if the system had this stiffness and you excited the system at 3 hertz, then the system will have very, very large amplitudes. In particular, if this system is in fact without friction and damping and is its mathematical idealization, then in fact the amplitude will go to infinity. Okay, so that's resonance. And then the second part is relatively straightforward. If k equals, so we are given some other value of k, what is the response amplitude? So response amplitude, there's a couple of different formulas. Is basically F naught divided by k divided by 1 minus omega divided by omega n whole square. F naught is given to be 100 newtons. K is given to be 5. 1 minus omega is 3 hertz, and then omega n is square root of k over m, which is square root of 5 over 1, which is square root of 5. So square root of 5 square, and that's the answer, right? So I'm just going to leave it at that. So it's 100 over 5, or 20, divided by 1 minus 3 square is 9, square root of 5 square is 5, 1 minus 9 over 5. well, we can simplify a little bit. 20 divided by 5 minus 9 over 5. 20 divided by basically 4 over 5, or 20 times 5 is 100 over 4 equals 25 meters. It's in units of distance, and it's going to be 25 meters for this particular problem. Okay, so it's just a huge spring mass system. Okay, so that's a simple example involving force vibration, the sort of very basic force vibration formula. Two things. One is that resonance means forcing frequency equals natural frequency. Second, the response amplitude has this simple formula. Recall that we actually derived the response amplitude formula for sine omega t, but it turns out that for these purposes, sine omega t is the same as cosine omega t. Everything remains the same. The response amplitude is exactly the same as before. Of course, if you want x of t, then it'll be actually minus 25 cosine omega t will be the x of t for cosine omega t. Okay, if it was sine omega t, it would have been sine omega t. If it was cosine omega t, it's cosine omega t. And there's always a negative sign here because it turns out that at resonance, the response is exactly out of phase with the forcing function, at least when there is no damping.